Okay, so as I was saying in the last video, space and time are unified under this concept of space-time, and it turns out that space itself, so the distance between points, and time, time, what we normally think of, 1 second, 2 seconds, 3 seconds, that the flow of time and the distance between points actually physically change to keep the speed of light the same. Now, in everyday experience, we don't, that's another thing. We'll get to that in just a minute. In everyday experience, you don't normally see this, okay? So this, for cars are traveling way too slow to observe, to be able to observe the fact that the speed of light is the same, because the speed of light is so much greater than the ordinary speed. Even race cars, for example, even like even spacecraft that are launched from Earth are not traveling fast enough to really notice this to any appreciable amount. You need really special equipment to be able to see this. But nowadays, of course, we can see this with relative ease. And just to go into a little bit of the history of this. Before Einstein came along, there were these two guys, Michelson and Morley, who I think they were both American, actually. I'm not sure about that entirely. But anyhow, they had performed an experiment where they measured the speed of light in the direction that the Earth is rotating, and then they measured the speed of light in the direction perpendicular, like towards the poles. And they thought, well, the Earth is moving so fast that maybe they would see a difference. And their experiment showed that there was absolutely no difference in the speed of light, whether it was in the same direction as the Earth's rotation, which is, by the way, also in the same direction that the Earth is moving around the sun, or perpendicular to that. So it didn't matter at all. And the Earth is moving pretty fast. I mean, certainly faster than anything could move, at the time, 100 years ago. And so that experiment, showed that there was no difference in the speed of light. And Einstein is said to have never heard of that experiment. That he based all of his ideas on trying to imagine the speed of light, from the perspective of a wave of light, of the movement of a wave of light. Could a one wave of light catch up with another wave? And that was really what led him to this idea of the speed of light. All right, so here's what happens. Let's go into this, as I was saying before, this idea. Let's say something is getting really close to the speed of light. So this is about 10% the speed of light. To really see these effects, you got to be something has to be traveling close to 90% the speed of light for people to actually notice the difference without special equipment to verify it. Which, again, we do have equipment that can verify this stuff now, but at the time, when Einstein first came up with that kind of technology didn't even exist yet. All right, so if something's traveling, 90% the speed of light, so 0.9 c, what happens is the distance. So let me get my mouse over here. The distance between 2 points would actually shrink, right? So if the distance was from where I have the mouse to the tip of the spacecraft, if that was the original distance that this person, standing aside would if this thing wasn't moving, if the spacecraft wasn't moving, they would measure this distance right here, let's say. And then if the spacecraft were moving close to the speed of light, again, about 90% the speed of light, or more, of course, so you can get up to almost the speed of light, then what happens is that distance right here would seem to shrink, would get smaller, right? And then something else happens that's really has taken on kind of a life of its own. So if somebody if let's say there was a big clock, a big digital clock on the side of this spacecraft, okay, and the people in, so this is important to understand this. It's really the idea of this, that there's no absolute frame of reference. Okay, so what we mean by that is, for people inside of the spacecraft that are traveling at 90% the speed of light, they don't notice any difference at all. They don't notice any length contraction. They don't notice any time dilation. For them, time is flying, is traveling along, just flying. 1 second after another, and so forth. Right? So just normal time between seconds. All right. So as this thing was traveling, at 90% the speed of light, this person that's not part of the motion here would look at the clock on the side of the spacecraft. Let's say it's a digital clock, and they would notice something very interesting. If they compared the clock on the spacecraft to, maybe they had a digital wristwatch on or something like that. If they look at their digital wristwatch, the watch on the spacecraft would be traveling, would be moving slower. So 1 second would go by on this person's watch on their hand, and then maybe 2 seconds would go by. Let's say 10 seconds goes by, and only 1 second would go by on the clock. Okay, that's on the side of the spacecraft. And see, the closer it's not linear at all, by the way. If you ever find that kind of thing interesting, the equations are actually not too complicated. It's a nonlinear. They are nonlinear equations, and so as you get closer to the speed of light, 1 second. So it's always convenient to just think about 1 second. Okay, so 1 second goes ticking by on the observer, the observer that's not moving along with the spacecraft. 1 second goes by on this person's watch, and then if this thing approaches like 99% the speed of light, or 99.9999% the speed of light, 1 second on this person's clock, on their wristwatch, would take, for 1 second to go by on the clock that's attached to the spacecraft, could take years. Literally 1 second could take years. And so and see, it's the thing is, it's not just a this is nothing about clocks. It doesn't have to do with, like I said, the people if there were people on the spacecraft, or the electronics on the spacecraft, it would not notice a single bit of difference. 1 second would tick by, another second would tick by, and so forth. But they could reach, the spacecraft could reach a speed by which, 1 second, for somebody not on the spacecraft goes by, and you could have a century, literally a century go by for the clock on the spacecraft, for this person to observe the clock on the spacecraft to go to tick to the next second. They're not going to be around for a whole century, but you get the idea. So the basic idea is, the closer and closer, and there's no restriction on how close you can get to the speed of light. It could be 99.999999, and you go as close as you want to the speed of light. Well, I take that back a little bit. It turns out that the closer you get to the speed of light, for a massive object to move closer and closer to the speed of light, requires more and more energy, real energy, right? And the energy, just like this time dilation, goes up dramatically the closer and closer you get. So the length contraction effect is observable, and as they get closer and closer to the speed of light. The time dilation effect is very, very much noticeable the closer and closer you get to the speed of light, and the amount of energy required to push the spacecraft closer, closer and closer to the speed of light, to go, 99.999 to 99.9999% the speed of light, requires enormous amounts of energy. And in fact, we've done calculations. You can do it yourself if you're interested. It would require more energy, to actually reach the speed of light. It requires more energy than there's available in the entire universe itself. So it would require an infinite amount of energy to get an object that has mass to travel at the speed of light. All right, so that is Einstein's special theory of relativity that he came up with in the year 1905. Again, very few people believed in back then. It seemed like some pretty weird ideas, but they turned out to be right, completely right. Every single time we've tested the special theory of relativity, it always turns out to be correct. All right, so it seems to be the way the universe works. The speed of light is an absolute constant of the universe. All right, so now let's go on. About 10 years later, Einstein didn't stop thinking about the universe. He came up with this idea of the general theory of relativity. So in the special theory of relativity, this thing right here, he's dealing with relative motion between objects that are traveling at non-accelerated in non-accelerated reference frames. That's the basic idea. In the general theory of relativity, Einstein realized that. Let me start with his original idea. Okay, so Einstein thought, okay, what if suddenly the sun were to just disappear? Okay, so this was one of his very many famous thought experiments that really led to some major changes in the ideas of physics. And so, if you imagine the sun suddenly disappearing, of course, we're not interested in the effects of light or heat or anything like that. That's not what he was thinking about in the general theory. What the general theory of relativity thinks about is the effect of gravity. What holds the planets in their orbits, of course, is gravitation, right? It's the gravitational force that the sun places on all the objects in the solar system, and that all these objects are orbiting the sun in some fashion. And so Einstein realized reasoned that if the sun suddenly disappeared, how long would it be before we would feel the effects of that? He realized, of course, the Earth would, if the Earth were traveling it's traveling almost in a circle, it would go off in a straight line that would be tangent to that circle. But he thought about it, and he said, well, would that happen instantaneously if the sun disappeared just suddenly, just magically? Would we feel it right away? And the answer turned out to be no. You wouldn't feel it right away. It would take about 8.33 minutes for us to realize that. Why 8.3 minutes? The reason, of course, is because that's the time it takes light, the fastest thing in the universe, to travel between the sun and the Earth, right? The speed of light. So he realized that the speed of light and also the force of gravity was dependent on the speed of light. All right. So here's another thing that Einstein, another famous thought experiment. If you were on an elevator, and the elevator, let's say, let's say the elevator isn't moving, it's just sitting on the surface of the Earth. You would feel your normal weight just fine. But if the elevator were being pulled upward